Starting with phosphorus. It is clear. Occurrence of phosphorus in bones, in fluorapatite, and all that was discussed in an earlier lecture. We come to straight away allotropes of phosphorus. Even that was discussed. Basically, the allotrope of phosphorus are the most known ones. Allotrope of phosphorus are yellow phosphorus, red phosphorus, and black phosphorus. See, one thing is, eventually all these allotropes will get converted into yellow phosphorus. See, what happens is, in yellow phosphorus, one P4 is connected to another P4 by weak van der Waals forces. Angle strain is 60 degrees. It's a huge strain of the angle, so that makes phosphorus yellow phosphorus very reactive. This is clear. If you keep it for many years, it may transform into what you call, and because it's reactive, what happens? One of the most important thing is phosphorus is kept under water. Yellow phosphorus. So let me be very clear. Yellow phosphorus, because moment it comes in contact with air, it immediately forms phosphorus pentoxide. Is this clear? So yellow phosphorus is kept under water. Why? Because P4 plus O2 forms P4O10. Okay. So it will form P4O10 or phosphorus pentaoxide. So therefore, it doesn't come in contact with air. It's kept under water. Is this point clear? Now, let us first look at the important differences between white phosphorus and red phosphorus. See, white phosphorus or yellow phosphorus is a yellow waxy solid, whereas this is a red brittle powder. Now, since red phosphorus is macromolecular, the structure is something like this, that you have one P4 connected to another P4 by a covalent bond. We say it's macromolecular, that's why the density increases. So density here is 2.2 grams per centimeter cube, whereas the density here is 1.8 grams per centimeter cube, because obviously the structure is one P4 is attached to another P4 by weak van der Waals forces. Melting point is 44 degrees centigrade. Okay, melting point here is 590. Boiling point is 280, whereas boiling point is 400 at 1 atmosphere pressure. See, the fifth point, yellow phosphorus is toxic. See, what happened was, originally it was yellow phosphorus which was used for making safety matches. And what happened was, the workers suffered from a disease called as phossy jaw. The jaw became very weak, and it wouldn't function, it wouldn't close and open. So therefore, the idea to transform yellow phosphorus to red phosphorus was a very important moment in science, because then all the matchboxes started started using red phosphorus. So while this is toxic, causes phossy jaw, this is non-toxic. Yellow phosphorus is soluble in carbon disulfide, this is insoluble in carbon disulfide, ignites in air at 35 degrees centigrade, it gives fluorescence. So when you boil yellow phosphorus in water, the fumes coming out, that is phosphorus pentaoxide, they appear as if they are burning. This is called as cold flame, because there is no heat attached to it. If you keep a match splinter, then nothing will happen. The matchstick will not get burnt. It is clear. It ignites in chlorine. It does not ignite in chlorine. It reacts with NaOH to form phosphine. We are going to come across this reaction. It does not form phosphine. Is it? Now we come to the third allotrope. The most important point from the examination point of view is that it is the most thermodynamically It is the most stable form. It is the most stable form thermodynamically. The second point is that it's a conductor of electricity. Unlike yellow and red phosphorus, it is a conductor of electricity. It is macromolecular in nature. It is macromolecular in nature, first thing. The fourth is, it's macromolecular in nature, and what we have is that it is insoluble in carbon disulfide. Insoluble in carbon disulfide. Fifth, so these are the points about black phosphorus. How can you write a fifth point? We can also say there are two types. There are two types. Alpha black phosphorus and beta black phosphorus. Okay, so this is about black phosphorus. So for us, what's important is most stable form. It is a conductor of electricity. So when you are talking of compounds of phosphorus, the first compound that we are talking about is phosphine. It is prepared by adding water or dilute sulfuric acid to calcium phosphide or aluminium phosphide. To calcium phosphide or aluminium phosphide or aluminium phosphide. See, what happens is calcium phosphide is Ca3P2 simply react with water. So what do you get? You get calcium hydroxide plus phosphine PH3 plus we can also have calcium phosphide reacting with dilute sulfuric acid and gives you calcium phosphate Ca3 calcium sulfate Ca3 CaSO4 calcium sulfate plus phosphine plus we have H2. So then you take aluminium phosphide and react with water. So what will happen? Or you can even react with dilute sulfuric acid, easier, faster. So what happens? You get Al2SO4 whole thrice plus PH3. See, aluminium phosphide, I mean, it's a very interesting case in India, in Bombay actually. What had happened was, one brother and sister who were in Qatar, they came here along with the parent. The parent had gone to the native place and they just came in and they were staying there, of course, when the parents went to the native place. It's a very interesting story. What happened was that they consumed the food and they died. So, the police actually, I forgot the name of the children. The police, caught hold of the parent thinking that you had committed murder and then you ran away to the native place. Even it was a Muslim family, so what happened was the body was cremated. You got the point. Now when they appealed to the court and all that, then what happened? A forensic examination was done. And one of the bodies, when the forensic examination was done, chemical test was done, they realized that there was trace of phosphine gas. And then when they tried to understand how did this happen, that the phosphine entered into the body of the A, they had realized that earlier on, just before they went to native place, they had given contract for pesticide. So that person who had done pesticide of the whole house, he had used aluminium phosphide, fumigant. He used aluminium phosphide, put acid, created phosphine, so that all the bugs, everything will die. But what happened was, the refrigerator was on. So phosphine entered into the refrigerator. It was absorbed by the chicken which was kept in the fridge. And this, when the children ate, they died. And after that, there was a ban on use of aluminium phosphide as a pesticide, as a home pesticide, for fumigating the houses. Very interesting case, I was just, a thought occurred that I thought I'll tell you, okay, what can happen, we just go on studying without understanding what is it useful for. Is this clear? So aluminium phosphide now is banned for, use as pesticides at home. Okay. Now the other method is yellow phosphorus. When treated with yellow phosphorus, when treated with sodium hydroxide, treated with sodium hydroxide, produces phosphine. So the reaction is somewhat like this, that is, we have P4 plus NaOH plus H2O. So it forms what? It forms phosphine PH3 plus NaH2PO2, NaH2PO2, sodium hypophosphite. Okay. So here you can see there is a change in the oxidation number, 0 to -3, and this will be +1. So this will be a disproportionation reaction, auto redox reaction or disproportionation. So what is a disproportionation reaction? Where the same substance undergoes oxidation as well as reduction, it's called as disproportionation reaction. So these are the methods of preparation of phosphine. We now look at some properties of phosphine. See, what happens is, phosphine has impurity, like how we have hydrazine is N2H4, it has an impurity P2H4. So moment phosphine comes in contact with air, what happens? Phosphine, because of the presence of this diphosphine, it immediately starts burning. Is this point clear? And that gives out a white smoke. Okay. So it's flammable. It itself is not flammable. It's flammable because of the impurity which is present. And it's a powerful reducing agent. Okay. So what happens is, suppose if you have, phosphine can be used to precipitate metals from their solution. So suppose if you have got copper sulfate, you pass phosphine, it forms copper phosphide, and this copper phosphide reacts with water present in the solution and you get precipitate of copper. Same case with silver. So in silver, in whatever form it is present, silver ion actually is present in solution, pass phosphine, you get silver phosphide which immediately decomposes to form metallic silver. So it's used to precipitate metallic silver. See, just like ammonium iodide. When you react ammonia with HI, you get ammonium iodide. Phosphine also reacts with HI to form phosphonium iodide. But if you put ammonia in water, it doesn't decompose. It undergoes hydrolysis. It's a salt of weak base, strong acid. Cation reacts with water to produce acidity. Whereas exactly what happens opposite is, if you put phosphonium iodide, that reacts with water to give phosphine. So this is one of the method of obtaining the purest form of phosphine. Is this point clear? A very interesting use of phosphine is in the setting up of Ohm's signal. See, in any port where the ship has to come in, what happens in the daytime, of course, there is visible light, it is easy to. In the night, if it has to come in, especially the problem was with when it was low tide, though it is a high tide, because the rocks, which are the big rocks, would be covered with water, and the captain will not be able to know. So those days they devised a very interesting idea to what you call guide the ship and show to them that there is a rock over here. What they used to do is, when there is a low tide, they used to take a boat, go up to the rock. There is already a hole drilled in that. So in that hole, they used to put a mixture of calcium carbide, CaC2, and calcium phosphide, Ca3P2. And when the high tide used to, what you call, because of high tide, water used to come into the hole and wet this mixture of calcium phosphide and calcium, what you call, calcium carbide. So what used to happen, because of calcium carbide used to react with water to form calcium hydroxide and C2H2, that is acetylene. So the acetylene gas used to bubble through the water up. Along with that, you had calcium phosphate, Ca3P2, that also reacted with water to form calcium hydroxide and phosphine gas. Moment phosphine came in contact with air because of the impurity of diphosphine, it used to catch fire. And if it is to catch fire, it is to burn acetylene. So what used to happen is, on the surface of water, there used to be a flame which was very visible to what you call the ship. And so they could navigate so that they are not what you call hit by rocks, and the ship hull will not get damaged. So this was one of the most interesting uses of phosphine. The second use, it is used for making organophosphorus compounds. So what do you mean by organophosphorus compound? See, organophosphorus compound means we are basically talking about pesticides. Pesticide and insecticide. See, most of the pesticides and insecticides are either compounds of sulfur or compounds of phosphorus. Then the third point is, it is used as, it is a strong reducer, it is used as a strong reducing agent. I told you, the metal ion can be reduced to its metal. Then it's also used as smoke screen. So phosphine burns, giving out smoke. So it's used in smoke screen in closed combat. See, what is smoke screen? What happens is, suppose when the commandos survey an area and they know that this is where the rebels or whatever people or the opposite army is there, then what they do, once they locate and they place their weapons, it is clear, what they do is they create a smoke screen using phosphor bombs. It's clear. So you know your angle properly that you're going to hit them. The other fellow will not be able to know because of the smoke screen. What is the location of the person who is firing? Is it clear? This is called as close combat. Especially in India, in Naxal operation, they use this kind of thing. So when they know that there's a group of Naxal over here, what they do is they surround them and then put the smoke screen and then they start firing. So the Naxal would be caught by surprise, which is the direction which they have to fire to neutralize this fire which is coming out. So when we talk of phosphorus, trihalides of phosphorus, the first point is all four trihalides exist. That's the first thing. So PF3, PCl3, PBr3, PI3 exist. Okay. The first point is PCl3, PBr3, PI3 are prepared by direct halogenation. Directly reacting with halogen. When we come to the other property, PF3 is a gas, whereas PCl3, PBr3 is a liquid and PI3 is a solid. Among this, actually, PCl3 is the most important trihalide. All are pyramidal in shape. They are pyramidal in shape. Okay. So I told you PCl3 is the most important trihalide. It is the most important trihalide. So it's prepared by directly reacting phosphorus with chlorine to form PCl3. Okay. This PCl3 reacts with water, and what does it form? It forms H3PO3. It forms H3PO3 and HCl. It forms H3PO3 plus HCl. It is called as either phosphorus acid or it is also called as phosphonic acid. So some books call this as phosphorus acid. Some old books call this as phosphonic acid. Okay. So this is about trihalides of, one more thing is PCl3. I mean, this will become a method of preparation of what you call PCl3 reacts with further chlorine and it forms PCl5. So this will become a method of preparation of PCl5. Pentahalides of phosphorus. So except for phosphorus pentaiodide, which does not exist, okay, phosphorus pentafluoride, phosphorus pentachloride, phosphorus pentabromide exist. This is a gas, whereas these two are solids. These two are solid. Is this clear? Now what happens? What are the properties that we can think of? See, PCl5 is the most important one. It immediately reacts with water to form POCl3 plus HCl. This POCl3, phosphoryl chloride, reacts further with water to form H3PO4 plus HCl. These are all, they are very, very, what you call, sensitive to OH group. Is this point clear? That's why we have OH of the alcohol being substituted by a halide, OH of the acid being substituted. They are all very sensitive to OH group. Is this point clear? Now what happens is, when you talk of structure, very important, this is a point very important from the entrance exam point of view. When you talk of structure, see, in vapor phase, PCl5 exists as trigonal bipyramidal. But what happens in the solid state? In the solid state, this question has been asked, it is ionic. It is ionic and it will have PCl4 plus and PCl6 minus. PCl4 plus and PCl6 minus. This is how it exists. Okay, so it will exist in this form. In case of bromide, in case of phosphorus pentabromide, see, these are all small points which are very, very important from the entrance exam point of view. In case of phosphorus bromide, see what happens is it exists as PBr4 plus and Br minus. This is because you will say why it's not PCl, PBr4 plus and PBr6 minus. See, accommodating 6 huge bromine atom becomes very, very difficult. Is this point clear? And that's one of the reasons. The steric hindrance is one of the reasons why PI5 does not exist. Is it clear? So I would request you to remember these two things. In the solid state, what is the ionic formula that we have. This is important from the entrance exam point of view. See, we are starting with oxyacids of phosphorus. So this concept will be there for the next topic also, oxyacids of sulfur. So let me first explain what you mean by oxyacid. See, what happens is, you have, suppose, a general formula MOH. So if M is a metal, so metal attached to hydroxyl group is called as hydroxide. Whereas if M is a non-metal, so non-metal attached to OH will be called as a oxyacid. It will be called as oxyacid. The simple reason is, in this case in water, the MOH bond breaks to give M plus OH minus. In this case what happens? It is the OH bond which breaks to give MO minus plus H plus, where it behaves as a acid. Now as far as oxyacids of phosphorus are concerned, what happens is, at the center is phosphorus. Tetrahedrally it is surrounded by at least one OH group. Okay, there could be other groups like PO group which can be present, okay, tetrahedrally. Then sometimes you have H group present. Is this point clear? You have OH as well as what you call H. Now there could also be in some cases a PP linkage, but then H will not be there wherever there is a PP linkage. Is this clear? Then whenever phosphorus POH is attached to a hydrogen, what happens is, these kind of oxyacids act as reducing agent. Okay. Then one more thing is, when you have an oxyacid where phosphorus has what you call +3 oxidation state, then what happens? It undergoes disproportionation. Is this clear? So these are some very basic points that we are talking about before we one more thing is, now when I say, let us look at another structure. So you have POH. So this is called as non-protonated oxygen. And this is called as protonated oxygen. So what happens, as the number of non-protonated oxygen increases, acidity increases. So which will be more acidic is one question. So you are supposed to know the structure. From the structure, there are two things you will know. One is, as oxidation, two things which decide the acidity. So points which decide acidity is, first is, as oxidation state on central atom increases, acidity increases. Second point is, if suppose both have nearly the same, if they are the same oxidation state, then what do we compare? As number of non-protonated oxygen increases, acidity increases. So these are the two criteria that we use in order to explain that question, which is which oxyacid of phosphorus is more acidic. So general rule which we have given how to answer the question in entrance exam. The first oxyacid that we are going to discuss is hypophosphorus acid, or it is also called as phosphenic acid. It's also called as phosphenic acid. The molecular formula is H3PO2. See, this is a very big importance, academic interest is because Moment we say H3PO2, now generally people think that the structure should be, there are 2 oxygen and 2 H, 3 H, so it should have somewhat a structure like this, and then so you have H2P, and then this will be H. So what happens, this gives a misconception that it's a dibasic acid. This structure is wrong. The actual structure has 2 hydrogen over here, so automatically what happens, it is a reducing agent, I told you. And then it has a P double bond O linkage and POH. So what can we understand from the structure? First of all, it is monobasic acid. It's monobasic acid. Second, what we can understand over here is, see, +1 +1 -2, and this is -1. So phosphorus has an oxidation state of +1 over here. Third, it is a reducing agent. It is a reducing. How is it prepared? It's prepared by treating barium salt with sulfuric acid to give barium sulfate and hypophosphorus acid. A simple method of preparation. So here, from the entrance exam point of view, you have to only remember H3PO2 should not be considered as a dibasic acid. It is a monobasic acid. Is this point? The second oxy acid that we are talking about is orthophosphorus acid, also called as phosphonic acid, or we have it is H3PO3. Okay, that's the molecular formula. So how do we prepare that? Simply you take P2O3 or its dimer P4O6, just add water, that you get H3PO3, or just add water to PCl3 and what happens? You get H3PO3. So when you talk of the structure, what happens? You have P double bond OH, OH and H. Is this clear? So here what happens is, what are the points that we can say? First and foremost, what we can say is, phosphorus has an oxidation state of +3. Second is, because of the presence of H, it's a good reducing agent. It's a good reducing agent. Third point is, it is dibasic. It is dibasic. Fourth point over here that we can talk about is, I told you that when you have a +3 oxidation state, what happens? It disproportionates. I told you in the beginning itself that oxy acids having +3 oxidation state undergoes disproportionation. So H3PO3, that is phosphonic acid, decomposes to form phosphine and orthophosphoric acid. So here we will have, what is this thing? This is +3 and this is -8. So this is phosphorus +5, this is phosphorus -3. So this can be a question in any entrance exam, that phosphonic acid or orthophosphoric acid disproportionate to give oxidation state. So it will be +3 and +5. So please pay attention to this. So this is all that we can think of. So it undergoes disproportionation. Auto-redox reaction, where it forms phosphine -3, and this is the advantage, because it disproportionately forms phosphine, which itself is a strong reducing agent. It increases the reducing property of orthophosphoric acid. There's pyrophosphorus acid. So in a pyrophosphorus acid, what happens is, we have a POP linkage, H4P2O5. So this is OH, this is OH, and then it has double bond O, H, H. So you have H4P2O5. Okay. So here, as you can see, what are the points that we can think of? There are 2 OH group. So first and foremost, it is dibasic acid. The second point is, phosphorus has an oxidation state of +3. Okay. Because of the presence of H, it's a reducing agent. And how is it obtained? It is obtained by treating PCl3 with, it is obtained by reacting PCl3 with H3PO3. PCl3 with H3PO3. So we get H4P2O5. Is this clear? Not much to talk about in this case. Only thing is you should know that which oxy acid has a POP linkage. So pyrophosphoric phosphorus acid, pyrophosphoric acid. So these are, when the word pyro is there over here, you should remember it as a POP linkage. That's the kind of question that they can ask, that how many PO linkage, POH linkage, pH linkage and POP linkage. So that calculation you should know. Is this clear? What we can say, I can write the calculation. What happens? It has 2 POH linkage, 2 P double bond O linkage, okay, 2 pH linkage and 1 POP linkage. 1 POP linkage. Phosphoric acid. The structure is something like this. We have a PP linkage, P double bond O linkage, 2 of them, and we have 4 POH linkage. So what does it tell us? It tells us that phosphorus has an oxidation state. So first is, there are 4 POH group, so it is tetrabasic. It's a tetrabasic acid. Second is, it has a PP linkage. Third, so that's why the word hypo. So pyro POP, hypo will be PP. Then we have oxidation state is +4. Very interesting thing about this acid is H4P2O6 can easily decompose to form H3PO3. It easily decomposes to form H3PO3 and HPO4. H3PO3 and HPO4. So this is phosphone. This will form phosphorus acid and metaphosphoric acid. So this becomes phosphorus acid and metaphosphoric acid. So remember, PP linkage. So which oxy acid? So what is the kind of question that we are trying to attempt? Which oxy acid has a PP linkage? Is this clear? So it will be hypophosphoric acid. Then which will have +4 oxidation state, which will have a PP linkage. Is it clear? H4P2O6, sorry, H4P2O6. So hypophosphoric acid on decomposition forms. So remember, it forms phosphorus acid and metaphosphoric acid. So this is how the 4 MCQs can be framed in this with regards to this oxy acid of phosphorus. What the most popular of all the oxy acids is orthophosphoric acid. It has a structure P double bond O, OH, OH, OH. So what does this tell us? It tells us that oxidation state is -1, -2, -3, plus -2, -5. So first is, it has phosphorus as an oxidation state of +5. Second, 3 OH group. It is a tribasic acid. It's a tribasic acid. Third is, it is a weak acid. It undergoes dissociation in 3 stages. What happens is, we have H3PO4 forms H++ H2PO4 minus, then H2PO4 minus forms H++ HPO4 minus, and HPO4 minus forms H++ PO4 minus 3. This is -2, I'm sorry. So literally this, I mean, you can, what do you call, you can, using pH meter, what do you call, estimate this, but this becomes very difficult to estimate. The reason is because phosphatine itself undergoes hydrolysis. Phosphatine undergoes hydrolysis to form metaphosphoric acid. So hydrolysis of the phosphate is a hindrance. Hydrolysis of phosphate ion is a hindrance. So even though we say it's a tribasic acid, technically we can only experience up to dibasic acid, is clear. But since Na3PO4, the salt is present, which when you react with NaOH, it reacts to form sodium phosphate. So we know that with reacting, when in neutralization reaction, it can show the tribasic character. Is this point clear? So basically it is a deliquescent solid. Deliquescent solid. Colorless deliquescent solid. But we also get this as a thick, it's also observed to be, it is obtained as thick syrupy liquid because of hydrogen bonding. Because of extensive hydrogen bonding. We now come to an interesting pyrophosphoric acid. See, what happens in pyrophosphoric acid is the structure is something like this. We have P double bond O, OH, H4P2O7. This is also called as diphosphoric 5 acid. So we have POH, P double bond O, OH. Since the word pyro is there is a POP linkage. Okay. So we have H4P2O7. So 1, 2, 3, 4, 5, 6, 7, H4. See, if you look at the point over here, first point that we can talk about is phosphorus oxidation state +5. It is supposed to be tetrabasic. That's why I've written over. Supposed to be tetrabasic, but what happens is so tetrabasic means you react with NaOH, the first H ion goes, then the second, then the third, then the fourth, then the fifth. Is this clear? Then the fourth. Okay, no, then the fifth. Fourth. So there should be 4 salts available with each H plus ion going dissociating. But what happens is, only 2 sodium salts are known. 2 sodium salts are known. Which are the 2 are known? Which are the ones which are this? The tetrasodium and the disodium salts are known. So monosodium, trisodium are not known. Is this point clear? So you can see only 2 salts are known. So this is one more indication that you should know. Is this clear? Now some of these salts from the pyrophosphoric acid clan, some of these salts are used basically for softening of water. It's not there in the syllabus, but it's better to know what it is used for. Okay, because they have phosphate groups attached, linked in a very complex structure, and that can actually act as, combined with calcium, get precipitated and remove or these calcium phosphate basically are soluble and will not form the scum. They will not form the insoluble salt basically. So that's where we use it for purification of water. Phosphoric acid, HPO3N. So this is the repeating unit. This is how. So it's a polymer, or it can be also cyclic. It can be either polymer or it can be cyclic. So if it's polymetaphosphoric acid, it could be cyclic in nature. In that case also, the basic repeating unit remains the same. So in this repeating unit, what do we find? It has a 3PO bond, 3POH bond and 2POP bond. Okay. And then what we can say, oxidation state will be -2, -1, 2, -2. So oxidation state here will be is +5. Oxidation state is +5. Oxidation state is +5. Okay, because see, let us look at it. This is -1 from here, -2, -2, -4, and then this will be, we take this as an example. That will be better. See, -1 from this oxygen, because -1 goes to this phosphorus, -1, -1 and -2. So total will be -5. So central phosphorus will have +5. This is also called as glacial phosphoric acid. This is also called as glacial phosphoric acid.